Thank you very much.
I am Ceren Dayar, physics teacher. I will be the moderator.
Okay.
We would like to thank you for accepting our invitation for this interview. It's a great pleasure to welcome you to Culture Schools.
Okay, thank you very much.
We have science high school students, Anatolian high school students, and middle school students with us today. They are excited and happy to make this interview with you. It's a great pleasure to say that they will visit Stockholm during the Nobel Prize Week and attend various Nobel Prize Week activities, including Nobel talks, lessons. We will be there.
Okay, great.
I want to introduce you to our distinguished guest, Professor Danielsson. He studied physics in Uppsala in mid-80s. He completed his PhD at Princeton University in USA in the early 90s. He worked as a fellow at CERN for 2 years. Then he returned to Sweden and Uppsala, where he works as a professor of theoretical physicist. He's a member of the Royal Swedish Academy of Sciences, the Royal Society of Arts and Sciences of Uppsala, and the Royal Society of Sciences of Uppsala. He's also the Secretary of Nobel Prize Committee for Physics 2022. Professor Danielsson's research deals with string theory with a special focus on applications in cosmology. He has devoted a great deal of his time to popularizing activities and is the author of award-winning books that have been translated into several languages. Again, thank you for being with us today, Professor Danielsson. Now our students are excitedly waiting for you to ask their questions. We will start. I think we can start. So the first question will come from Computer Science High School student Emre Kızılderili. Emre.
Hello.
Now
my question is about quantum entanglement, which is the subject of this year's Nobel Physics Prize. What do you think new studies on quantum entanglement will contribute to physics and technological improvement in the future?
So if I heard it correct, how the prize this year will contribute to technology and development and in the future? That was the question. Okay. It's a very good question, because this prize, you could say, has two aspects. On the one hand, it's awarding really important discoveries and measurements having to do with our fundamental understanding of nature and quantum mechanics, of course, which is very, very interesting and has been something which has been discussed over the decades, actually, how to interpret quantum mechanics, what are the even philosophical consequences. It goes back to the 1930s, so it's something very, very fundamental. But on the other hand, it's also a prize which deals with physics, which can lead to very exciting applications in the future. And this is also part of this award, how to develop such techniques. And in particular, there are two applications which are discussed, which have to do with quantum mechanics at the borderline between the microscopic and macroscopic world. One of them is cryptography, and that's also part of this year's prize. One of the laureates, Anton Zeilinger, has used these entangled photons to show that you can actually, in practice, use that to transmit messages that cannot be, no one can eavesdrop without being spotted. So that's sort of the idea here. So it could be that in the future, entanglement can be used to transmit coded messages all over the world, and even partly at least replace the current mathematical crypto. So that's one possibility. Another one, which is really much more exciting, even more exciting, and it's sort of in this general field of physics, that's quantum computing, because that again has to do with quantum mechanics at macroscopic scales, and this prize is about that to some extent. So how to apply quantum mechanics not only in the microscopic world within atoms and in particle physics and so on, but also how to use it technologically at large scales. That's something which this prize is sort of pointing towards.
There are already some applications in the usage, right? So banks in the transaction can use quantum cryptography, right?
In principle, even though it hasn't really been, it's not really used very much as yet, but it has been tested in some cases. And indeed, as is part of this prize, it was possible to even send messages like that between continents, actually. So it's something which really, really works.
Yeah, thank you very much for your answer, Professor Danielsson. Our next question will come from Kültür College Middle. Paksoy, Parla, we are listening.
While you were investigating about the universe, what was the most terrifying or devastating thing for you?
So what was most terrifying? Actually, I mean, some people, I understand your question, because some people get scared when they go out the dark night and look at the sky. I never get scared of that. I mean, I find it fantastic and fascinating. And I got interested in astronomy and physics and cosmology very early on. And I remember that I sort of made a promise when I was 7 years old that this is what I will want to do with my life. I want to study all of these things. So I really cannot say that anything really terrifies me in that sense, although you get very humble sometimes, and it's overwhelming to some extent, and this feeling that there are these answers out there even if we don't know about them, that's something which is really, well, again, it's not, I mean, it makes you humble, let me put it like that. Well, maybe I should be terrified. I mean, all of these black holes and things which I'm studying, but I cannot say that I'm that. I'm too fascinated and too interested in these things to get scared.
Fascinated rather than terrified.
Yes, absolutely.
Now, our third question will come from Kültür College Middle School student Elif Semercioğlu. We are listening to you, Elif.
Hello. Which one is the best scenario in terms of the solution of the dark matter and the dark energy?
This is really one of the most difficult and important questions in fundamental physics at the present. And if we take dark matter, the most popular proposal for dark matter is that there's some kind of unknown particle, which can collect into big clouds around the galaxies and through its gravity influence the motion of the stars, and also in a similar way affect and play a part when galaxies formed in the early universe. It really seems as if you need something like that. And the most popular idea is that there is some kind of a particle. And the most popular kind of particle are the supersymmetric relatives to the particles known in the standard model. So these are hypothetical particles which comes very natural from a theoretical point of view. And LHC, the big accelerator, has been looking for them, not seen anything. we have been searching for them using detectors here at Earth, because if there are these supersymmetric particles flying around in the galaxy, we should be able to trap them here down at Earth. We haven't seen anything. Particles like that could also collide and gather and be converted into radiations of different kinds, which we could detect, but we haven't seen that either. So there are no signs of these particles, which in some sense might make you a little bit worried if you believe that this is the explanation. I think that many people are still believing that these are really the supersymmetric particles. There are some other candidates as well, but there are even people that think that maybe there is something deeper going on. Maybe it's even something which is wrong with the theory of gravity, and there are some modifications there, even though that is much more exotic. But again, I think that most people believe that it's some kind of new particle, and apart from the supersymmetric particles, it could be some kind of very heavy kind of neutrino. That's another proposal. But to be honest, I don't think that we actually know, and there is no real good agreement about what the explanation would be. If you had gone back like 20 years in time, most people would have put a bet on the supersymmetric particles. But given that we still haven't seen them, I think there is more of a disagreement at the present time than it has been before. As far as the dark energy is concerned, it's even more difficult to understand what it is. I mean, it's some kind of energy there in the darkness which makes the universe accelerate. But what it is, very difficult to know. I work in string theory, and there dark energy, or cosmological constant, as you sometimes calls it, it's really one of the most important and most difficult challenges, because it turns out that even if you in string theory can construct models which have a dark energy, and to do that you need to make use of the extra dimensions and various fields which lives in the extra dimensions of string theory, it seems as if you are able to generate through these higher dimensional constructions a cosmological constant. But in most cases, these models have mathematical problems. They are unstable, and the solutions cannot really be trusted. So I cannot give a good answer even to that question. So what I can say is that we know what about 5% of the universe is. The other 25% in the form of dark matter, and about 70% in the form of dark energy, we simply do not know.
I didn't catch your last word, but I think you're finished, right?
Yes.
Thank you, Professor Danielsson. Now, our next question will come from Kültür High School, Science High School student, Eda Su Gürler. Eda, we are listening to you.
Hello. Firstly, thank you for sharing your research with us. According to your blog, how do you plan to announce your studies on nature and physics to this audience?
Sorry, I didn't hear quite.
Can you hear me well now?
I hear you, yes.
Okay. Firstly, thank you for sharing your research with us. According to your blog, how do you plan to announce your studies on nature and physics to this audience?
How I plan to
I mean, she means how do you plan to deliver your studies on nature and physics to maybe larger audiences? Maybe in the world.
Yes. I see. Okay. So yes, I mean, I obviously what I'm doing with my research, then together with colleagues, then I write papers which are published in scientific journals. So that's sort of how the research is done and distributed. But then in addition to that, I find it very important to also try to tell sort of more the general audience what I'm doing or what science is about in general. And that means that I actually have written a number of popular science books as well. These books are mostly in Sweden, but in Swedish, but a couple of them have also been translated into other languages. And one of the book, a book which I wrote 2 years ago, that book is now being translated into English, and it will be published this February by a New York-based publisher. It's called The World Itself. And it's a very somewhat more philosophical book about the science and sort of I'm sort of presenting a worldview which I've been sort of developed not only through my studies in physics, but also thinking about its relation to other fields of science and not only science. And it's also translated into other languages, like it's German, Portuguese, Chinese, Korean, a few different, we'll see where it ends. But anyway, I find it, in fact, very, very, I really like to do that. I mean, to write also for another audience where you can also put things into a much bigger context. So I try to write books, I give lectures, and yeah, that's sort of how I try to communicate.
Maybe your latest book will be translated in Turkish in the future.
Perhaps. Yeah, perhaps. I don't know. By the way, I also wrote even later book, which just appeared a couple of months ago. It's only in Swedish so far, but that's a book about which it's sort of a little more science fiction kind of book, where there is an organization of aliens who are writing a book for us here on Earth, telling us what we need to know in order to survive.
Your latest book is The World Itself, Consciousness and Everything of Physics.
Yes.
And in the it is stated on the book cover that we cannot fully comprehend the universe before we fully understand consciousness and limits of the mind. Limits of the mind. Can you please elaborate on this?
Yes, I can do that. I think that one of the most one can do it. Okay, I think that I'm sort of a naturalist. I think that that the world is one in some sense. That everything in some sense is physics, and that consciousness is also a physical phenomena, but something that we cannot understand. And we cannot understand it using the kind of science that we have today. And we cannot even be sure that we will ever understand it. But what's very important for me in the way that I view nature is that I'm part of it. And it also means that what I see and the models that I set up and all the mathematics that I use are really tools for me as a biological organic being to understand a universe which I am a part of. And that's really what was sort of the main theme of the book. And also pointing out that maybe the most difficult problems is not what happens in black holes at the origin of the universe, but it might be us as organic and thinking being, which also are part of this physical universe.
Okay, so we can thank you for your answer. We can now continue with the next question. This question will come from Kültür Anatolian High School student Fergan Doğu Çoban. Fergan, we are listening to you.
Hello, my question is Is there any mathematical equation that models all known forces of nature possible?
So any mathematical equation that models...
Can you repeat your question, Fargan?
Okay. Is there any mathematical equation that models all known forces of nature possible?
That models all known forces possible in nature. Is that what you were asking, if there is such an equation? Okay. Well, I mean, one could say that within particle physics, there is a set of equations which describe many different kinds of forces, and these are the so-called gauge theories. And that's really a mathematical framework which can describe all sorts of different kinds of forces. And in our world, there is only 3 different forces which we actually know about. And that's the electromagnetic force, and it's the weak force, and it's the strong force. And these 3 forces are all part of can be described as gauge theories. So gauge theories, that's broadly speaking, that sort of is the tool that we use to describe forces. And one could, in some sense, say that that sort of includes all kind of forces that we could really imagine in particle physics. And it's different kinds of mathematical structures. And obviously, in our real world, there will be only a few of those which actually will correspond to something real. So yes, one could say that the gauge theories would be the answer to your question.
Thank you for your answer, Professor Danielsson. Our next question will come from Kültür Anatolian High School student Emine Bilge Göktaş. Emine, we are listening to you.
First of all, thank you for giving us this opportunity. My question is, what is the theory of quantum gravitation regarding black holes, and what do you think about it?
Okay, so going back to the 1970s, or even before then, actually, we have known that there is a problem in putting quantum mechanics together with gravity to get some kind of a consistent theory. There are really paradoxes that appear. And this is particularly true when it comes to black holes. And this is what Stephen Hawking discovered theoretically in the 1970s. So what he noted is that the black holes, due to quantum mechanics, will emit radiation. So this is very different from what we expect from general relativity, in the sense that in general relativity, a black hole can only grow in mass and nothing can escape. Now, these things leads to actually two paradoxes, where it seems as if quantum mechanics and general relativity are not consistent with each other. It's called the information paradox. And it has to do with the fact that in quantum mechanics, information cannot be destroyed. It can only be hidden and distributed in ways that it's difficult to retrieve it. But information cannot be destroyed. On the other hand, in general relativity, that's with black holes, that seems to be something that must happen. And Hawking drew the conclusion somehow that the very basic laws of quantum mechanics had to be violated when you combine quantum mechanics with general relativity. So that was his sort of take on the problem. Now, this information paradox has been studied ever since. And in particular, in string theory, one has come up with proposals which sort of rescue quantum mechanics so that information is not lost, not even when you have black holes. And this has been debated back and forth for a couple of decades. And some people believe that the problem is in principle solved. even though a lot of technical and mathematical work remains, and others are more skeptical. And some people even believe that this problem is so difficult, and this disagreement between quantum mechanics and general relativity is so severe that we may not even be sure that black holes have the structure that we now commonly believe that they have with their horizon and singularity, that in fact there is something new happening a bit before you dive into the horizon. Now, this is of course very speculative, and I also are thinking about exactly these problems. But what makes all of this so exciting now is that regardless of what you believe about the theoretical proposals, there are possibilities maybe to be able to start to actually test some of these ideas, since we are so much better now in examining and studying black holes. We have gravitational waves from colliding black holes, and we also have these very exciting pictures, real pictures of black holes taken by the Event Horizon Telescope. And if these observations can reach a high degree of precision, then you could start to check whether black holes are as we usually think they are, or whether there are some new effects there which then turn out to be necessary in order to remove the paradoxes of quantum mechanics and general relativity. But still, we don't know. But my general feeling is that we will not solve these problems just by theory alone. We need to have this exchange between theory, experiments, and observations to make real progress. And there is some hope of that in the near future.
Thank you. Our next question will come from Kültür 2000 Science High School student, Ceylin Akdoğan. Ceylin, we are listening to you.
Do you think that string theory explains the universe with a single equation?
I think that string theory is probably a necessary next step, because it so naturally follows from all that we know about particle physics, quantum mechanics, quantum field theory, and general relativity. It's very difficult to escape from going down that route. On the other hand, I think that even if we were to make great progress explaining unknown things like dark energy, fully understanding black holes, making new predictions, and sort of really join quantum mechanics and general relativity together with string theory, I cannot think that that would still be the final answer. I think that this is what we're doing now with science and fundamental physics. It's a project that will continue and continue, and we will discover new things. I mean, before quantum mechanics and relativity in the beginning of the 19th century, many thought that they sort of had it all with Newtonian mechanics. And then, of course, if you move on into the 19th century, Maxwell's equation for electromagnetism, and everything was in place. And then, as we know, relativity and quantum mechanics were discovered, and a whole new world opened up. And maybe string theory now opens up a whole new world like that again. But then I'm sure even if we got all of that in place, there will be some things which still doesn't quite work, and there will be new discoveries to be made. And this might just continue and continue. And it's not clear that we as human beings are clever enough to ever come to the end of the road, if there even exists one.
I'm sorry, screen freeze, and we didn't.
I think I'm not sure, but I'm not sure if it's mine, but it's usually your screen that freezes, not the students. I can see them moving around, but you freeze sometimes. But maybe I freeze as well. I don't know.
Okay. I think maybe there's a problem with my connection. Thank you for your answer, Professor Danielsson. We can continue with our next question. It will come from Kültür 2000 Science High School student, Doğa Taştan. Doğa, we are listening to you.
While reading your research, something caught my attention in your article, Gravitational Waves in Dark Bubble Cosmology. I want to ask you what exactly is homogeneously and isotropically expanding universe?
Okay, so homogeneous and isotropic, these are sort of simplifications one uses to describe the expanding universe. It just means that on large scales, the universe is homogeneous. That means it has sort of the same density everywhere. Isotropic means that it looks the same in all directions. So it's really just a simplification, and that seems to be more or less a very good approximation to our universe. That it's like that when it expands. So it's just a simplification, which is usually assumed.
For your answer.
Yep.
Our next question will come from Kültür 2000 Anatolian High School student Naz Tutar. Naz?
How do you see the possibility that the data obtained by the James Webb Telescope may change our explanations of the known universe?
I think that the Webb Telescope is okay. So I mentioned previously that there is hope for new input, like gravitational waves and event horizon telescope pictures of black holes and so on. The Webb Telescope is another opportunity to really get new input. And it's simply because it's such a big telescope and it will be making observations that never have been made before. So we cannot really predict what it will see. And it will look into the sort of the dark ages where the first galaxies formed. And that might also involve the role of black holes, because we have black holes in the center of all galaxies, and we don't really know from where they come. So all of that is very exciting. It could be really new fundamental physics that the Webb Telescope might discover. Then, of course, there is another thing which is troubling some cosmologists. And that is that on the one hand, we have the dark energy presently, which we don't know what it is, but it explains the acceleration of the universe. But there is also a mismatch between measurements made in the late universe and in the early universe when it comes to the rate of expansion of the universe. There's something which doesn't quite work out. So there seems to be possibly something new happening in the early universe, which we don't quite understand. So having an instrument like the Webb Telescope that in a new way can study the early universe and see what's going on there is, of course, very, very exciting. So we don't know, but it's often like that. When you have a new instrument with capabilities which you haven't had before, then there can be these new surprises which really speed up the development of a scientific field. Then, of course, the Webb Telescope is interesting in other ways. I mean, looking for life on other planets, which is, of course, a completely different story, but something very, very interesting and fundamentally important as well. So, yes, I have great hopes for the Webb Telescope.
Thank you for your answer.
Our next question will come from Kültür student Can Ugan.
My question is, how did you realize that you were interested in physics? And if you did not work in the field of physics, in which field would you like to work?
Okay, so I started out very early on, and I was very interested in science, really, well, as far back as I can remember. So I was particularly interested in, I was raising butterflies and collecting strange animals in a pond nearby and looking at them and all sorts of biology very early on. And then as I told you, when I was 7 years old, I promised I'm going to be a physicist or astronomer. And then there were some other fantastic experiences I had later on. When I was 12 years old, I saw a comet that was, I still remember it. I mean, the shock when I first saw it, I couldn't imagine something as spectacular as that. So I really had several experiences like that early on as a kid, and I grew up in a small village with a dark sky, and I had nature all around me. But you had also a second question, and that is, what would I have done if I did not go into physics and astronomy? I would probably have done something in biology, I think. Because in some sense, even though I'm a physicist, I would even sort of sense that maybe the most difficult physical problem has to do with biology and maybe even consciousness. So most probably I would have done something like that, but I don't regret my choice.
Yeah, I'm very interested in biology too, and thank you for your answer.
Okay.
Be a biology class. He loves biology. So I have another question, Professor Danielsson. Which scientist did you take as a role model or example before starting this profession?
I'm not sure that I ever had a role model like that, but there are some scientists which fascinates me, and maybe the one which fascinates me the most, because I think he's the one who took the boldest and most surprising step. That's actually Newton. So it's not anything original, but it's really Newton, because before Newton, nobody really were able to apply mathematics to physics in the same way. I mean, of course, I mean, Galileo did it to some extent, and Kepler and so on. It was used, but Newton, in some sense, even developed part of the modern mathematics and applied it to the physical world, and also discovered that there's the same laws of nature that govern physics down on Earth, like the fall of an apple, as it is to describe the motion of the moon on the sky, connecting everything together. I mean, this is absolutely incredible, and something which is even, it's a bigger step than even what Einstein or anyone else did after him. So I think that this is something which is so fascinating, how a single individual can make all of those discoveries.
So we have a lot of students love physics, and maybe they want to pursue a career or academic career in physics. So what would you say to those students who loves physics and who love to study physics in the university?
I think it's that you should be driven by your curiosity and make sure that you enjoy what you are doing, really. I mean, it's something which, for me, the motivation has been this curiosity. It's something that has meant so much for me. And it really has, for me, an existential dimension. And I think you should try to make sure that you also think about science in general. I mean, if you have curiosity for physics, it's natural that you have curiosity for other neighboring fields as well, so that you sort of you feel at home in the universe in some sense. Then, of course, for me, and maybe the reason why I chose physics was that I found mathematics so fun. And that's also very important if you go into physics, at least the kind of theoretical physics that I'm working on, that you really love math and you practice and try to understand things really carefully and don't give up before you really understand. You should of course not get stuck. You need to move on, and then you might need to go back and try to solve the problems that you left and so on. But it's difficult to give any advice, but general advice. But I think the important thing is not just to have some kind of a goal in the future that you are going to be this or that and get that or that position. This is not the set of mind that you should have. Your focus should be on what you are doing, the content of the subject. That is what should drive you forward, not any faraway goal of being a professor or whatever. It's not that. It's really to enjoy the thing that you are doing. Then these other things will come as well. But you shouldn't get distracted by that. You should be focused on what you are doing and enjoy it and so on.
So enjoy, practice, and think deeply of simple things, I guess.
I think so, indeed. And again, mathematics, it's kind of it's a craft. It's something that you need to be able to do in order to. It's a language that you need to not only learn to read, but also learn to speak, in a sense.
I have one last question. So this year, 3 distinguished scientists are awarded by Nobel Prize for their works on quantum entanglement. So as a theoretical physicist, scientist, are you specifically excited by this prize? What would you say?
Well, as I'm part of the Nobel Committee and selecting it, I'm of course excited by prize every year. I have to say that. Maybe excited in different ways. And what makes this year's prize make me so excited is that and I think that was more or less the first question also, that it combines, on the one hand, very fundamentally important measurements and tests of quantum mechanical predictions with it sort of also, so it points backwards in that sense, but it points forward in the sense that it also promises new and exciting technological applications. So it's an example of how the most fundamental physics that you can imagine can have important consequences for what will have around to shape the future world. So I think that this combination is something which makes this year's prize so special.
Thank you very much. Again, we would like to thank you for being with us today, for accepting our invitation. It was a great pleasure and honor. Thank you very much, Professor Danielsson.
Yeah, and have a nice trip to Stockholm, and I hope you enjoy the days there. So when are you coming, and for how long are you staying?
December 7th.
Okay. Mm-hmm. And then you stay
for 5 days, okay, until Sunday, and Sunday we will leave.
Okay. And so you will go to the Nobel lectures then?
Yes, we will listen Nobel lectures, and also we will go to Nobel talks, and some of the students will go to a concert, Nobel concert.
Ah, okay. I will do that too. So maybe we'll see each other.
Ah, yeah, maybe we can see you in person.
Absolutely. Hope so.
Thank you very much again.
Okay, thank you.
So maybe we'll see you there.
Absolutely. Bye-bye.
Bye-bye. Thank you for everything.
Bye-bye. Çık. Bitti.